Welcome to the Explainer. Have you ever really stopped to think about what's going on inside your phone? Like, really think about it. How does this chunk of metal and glass, how does it understand a photo or a video or even a complex thought, all with just electricity? It feels like magic, right? Well, it's not, and we're going to break it down. So, what's the secret? Well, get this. The entire digital universe, every app, every photo, every song, it's all built on a language that has only two words. Just two, on and off. That's it. That's the whole foundation.
Okay, so how on earth do you get from a simple on-off switch to, everything else? Well, to figure that out, we've got to learn the computer's secret language. And that language, it's called binary, or if you want to get technical, base 2. It is literally the foundation for everything a computer does. See, we're all used to counting with 10 digits, right? 0 through 9. But a computer, it only has 2 to work with. A 0, which means off, and a 1, which means on.
So on the left here, you see our everyday system, base 10. You know it well, the ones column, the tens column, hundreds, and so on. But check out the right side. That's the computer's world, base 2. The columns are a little different. We've got 1s, 2s, 4s, 8s, 16s. You starting to see the pattern here?
And that right there, that's the whole secret. We count in powers of 10, computers count in powers of 2. It really is that simple. Once that clicks, you're already halfway to thinking like a computer.
Okay, so we get the basic idea, but how do we actually read this stuff? Let's dive in.
All right, so in the computer world, you'll hear the term byte a lot. A byte is just a group of 8 bits, 8 of those little on-off switches. And each of those 8 spots has its own special value. Starting from the far right, we've got 1, and then it just doubles each time you move left. 2, 4, 8, all the way up to 128. Let's actually try to read one. Look at this binary number, 0, 1, 1, 0, 1, 0, 1, 1. The rule is super simple. Wherever you see a 1, you take that column's value. So in our case, we've got a 1 in the 64 spot, the 32 spot, the 8s, the 2s, and the 1 spot. Anywhere you see a 0, just ignore it. Now all we do is add them up. So 64 plus 32 plus 8 plus 2 plus 1, and that gives us 107. See? Not so scary, right?
Okay, so this system is perfect for a computer. It's all it knows. But for us, for humans, it's kind of a nightmare. I mean, it's just so long.
Just look at that string of 1s and 0s. Can you imagine trying to type that out without making a single mistake? No way. It would be a total disaster. So naturally, the smart folks who build this stuff came up with a much better way.
And that better way is a system that's basically a human-friendly shorthand for all this binary.
Say hello to hexadecimal, or just hex for short. Now this is a base 16 system. So wait, how do you get 16 digits when we only have 0 through 9? Simple. You use 0 through 9, and then you just borrow the letters A through F to stand in for the values 10 through 15. Clever, right? And here is the absolute magic of hex. Because 16 just so happens to be 2 to the power of 4, it means that every little group of 4 binary digits maps perfectly to just one single hexadecimal digit. That's the key. That's what makes it so clean and easy for us humans to read.
Now, you might be thinking, okay, that's cool, but this is all just abstract nerd stuff, right? Wrong. I guarantee you see hexadecimal every single day. Let's go find some in the wild.
Seriously, hex is everywhere. You see it in the color codes on websites. It's used for the unique ID on your phone, your laptop, every device on your network. And for developers, it's an absolutely essential tool for peeking under the hood and seeing what a computer is really thinking.
So this right here, this is what's called the memory dump. Think of it like a brain scan of a computer at a specific moment in time. For a programmer trying to hunt down a nasty bug, this is invaluable. Now, imagine trying to read this wall of text in pure binary. Yeah, forget it. Impossible. But in hex, it's still complex, but it's actually doable.
Let's look at some more common examples. You've probably seen a web color code like #FF0000. That hex code is just a simple instruction. It's telling your browser, hey, give me the maximum amount of red, that's FF, and absolutely 0 green and 0 blue, that's 0000. Or what about a device ID, a MAC address? That string of hex gives every single device on a network a unique fingerprint. And that first part, O1C B3, That's actually a code that tells you the manufacturer. In this case, it's Apple.
All right, so we've got numbers down. But what about negative numbers? That's a whole other can of worms. I mean, how can a machine that only gets on and off possibly understand the concept of less than zero?
Okay, so in the computer's world, there are basically two flavors of numbers. First, you have unsigned numbers. These are simple. They only represent positive values. So an 8-bit unsigned number can be anything from 0 all the way up to 255. But then you have signed numbers. To make those work, we have to sacrifice one of our bits, the very first one on the left, to act as a sign bit. If that bit is a 0, the number's positive. If it's a 1, the number's negative.
Now, the first few attempts to get this right had some issues. Early methods like sign magnitude and one's complement had this really weird and inefficient flaw. They ended up with two different ways to write the number 0. You had a positive 0 and a negative 0. This just made the math way more complicated than it needed to be and wasted a valuable number.
So the engineers came up with a really brilliant solution that is now the universal standard. It's called 2's complement, and it's just elegant. It's super efficient for the computer's processor to work with, and, this is the big one, it has only one single, unmistakable way to represent 0. Problem solved.
So how does it work? It's actually a pretty simple 3-step trick. Let's say we want to make negative 20. Step 1, you start with a binary for positive 20. That's 000101100. Step 2, you invert all the bits. Every 0 becomes a 1, and every 1 becomes a 0. And finally, step 3, you just add 1 to the result. And voila! That final number, 111011100, that is exactly how a modern computer represents negative 20.
And that's pretty amazing when you think about it. From a simple, humble on-off switch, we have built this entire sprawling digital universe. Everything from sending a text across the planet in an instant to building entire virtual worlds, it all traces back to that one simple concept. It really makes you wonder, doesn't it? What are we going to build with it next?